and especially Mr. Jonathan Anderson. He'll be talking to us about Capsicum and how this can make our lives, or at least our computer, a little bit more safe. Thank you very much.
Thank you. Can you all hear me in the back? Yes? All right, excellent. So if I could ask you by a show of hands, how many people in this room watch video in a web browser ever? Okay, now let's add to those people the people who use web pages that involve JavaScript or images. Yeah, okay, that covers pretty much everybody. Now, of the people who do any of those things, how many of you use online banking in the same browser? Ah, very many of you. Okay, so hopefully this talk will be of interest. So this talk is about Capsicum, which is a security framework that we've implemented in FreeBSD. This work was done with Robert Watson, who is kind of my boss at the University of Cambridge, Pavel Davidek, who's a FreeBSD committer who's doing lots of the work, Ben Laurie, David Drysdale, and Chris Kenaway are all at Google and have done various things, technical and otherwise, for us. So here is the motivation. Here's the problem. So I have a web browser, and I do lots of different things in said web browser. You can see up here, I'm just looking at what looks like a pretty boring web page, even though it's kind of a complicated JavaScript application. This is definitely a complicated JavaScript application. Over here, I'm watching some video, and I'm doing video decompression with a codec that was written by who knows who's interested in performance, performance, and performance. And you'll note security is not on that list of 3 things they care about. And then down here, I'm doing something very sensitive, my online banking. And the trouble is that whenever there is an exploit in some video codec, well, it could have access to all kinds of crazy stuff. And that is why we try to employ sandboxing, to separate the various pieces of things that you might like to do, particularly in web browsers, but also in lots of other kinds of applications. But web browsers are kind of a natural example, so I'll probably talk mostly about those. So the concept of sandboxing is that you take every tab, logically, it doesn't actually work quite like that, but logically you take every tab, you stick it in its own little box where it can build its own sandcastles or it can knock its sandcastles over or whatever, but it doesn't have the ability to go into the next sandbox and knock over somebody else's sandcastles. So when you get an exploit and you have malware, well, it doesn't get outside here. So they can mess up my video rendering, but that's not a big deal. So that is conceptually very simple. And now the question is, how is this actually implemented? The answer is, prior to Capsicum, in a bit of an uneven way. So let's see. Let's look at the conventional picture of a stack. So we have hardware and there's kernel. On top of that, we're running a bunch of applications. But the key thing is that these applications are running on behalf of users. So here, if I'm using LibreOffice and I want to open a document, then this, well, actually, this is a Windows dialog. Nobody in this room would see that one, obviously. But anyway, the point is that this application is allowed to do anything such as open files that I, as the user, am allowed to do. It is operating on my behalf with what we call ambient authority, the authority that I would normally have when I'm using my computer. And this means that if you have trouble in an application, well, it can do anything that you can do. So in practice, let's see. Here we go. Here we have, again, this decomposed view of a web browser where not only, if absent sandboxing, not only is malware able to do things in another tab in your web browser, it is in fact allowed to do anything that you, as the user, have the authority to do on your own computer. And so this is the discretionary access control model, where things have owners, and there are people, and then the users, who may or may not be people, can do whatever they like to anything they own. And that is DAC. So what a browser like Chromium does, in order to try and address this, is to split itself up into a bunch of little processes. So you have the browser process, and then you have several renderers. And the browser runs with the normal ambient authority, and the renderer processes run with some kind of protection put underneath them to stop them from doing stuff. Now, stuff will vary by operating system, and even within operating systems, depending on the sandboxing technique, stuff will be defined very, very differently. But this is conceptually the model. So what Capsicum is it's a mechanism for implementing that sandboxing regime. So applications that are big applications can split themselves up into little parts, and each little bit can have just the least privileges that it requires. This is targeted on FreeBSD, mostly because, well, we're FreeBSD committers and very familiar with it, but also there's a potential for this stuff to get adopted in products by companies like who build products on FreeBSD. And the goal of Capsicum was to take an older literature on capability-oriented security and apply it in a real Unix operating system that has real applications and run real stuff today. Often many security historically, capability systems were an active field of research, but you don't see a lot of them running today. And then on the other side, we have sort of the Unix model, which, well, it's not quite as locked down as the capability-oriented security model. So this was done in an academic context. We did a bunch of work, but it wasn't just a prototype. We have actually pushed this upstream into FreeBSD. So how does it work? And I'll say, do stop me at any time in the middle for questions if you like. Put your hand or wave furiously if I don't notice you. It's kind of a big room. So what is a capability? A capability is a token that says I'm allowed to do something, and it's an unforgeable token. Now people often use a crown as a sort of analogy for this. Some guy walks into the Belgian parliament and says dissolve parliament, and you're like, well, he puts a crown on and says sudo dissolve the parliament, and you're like, okay, yes sir. But it might actually be more helpful to think about a subway token. So a subway token, or in fact a beer token at the FOSDEM beer event on Friday night. A token is something that you can exchange for one beer at the delirium thing, or one ride on the subway. And critically, it doesn't depend on who you are. You don't show your passport in order to get on the subway. It doesn't depend on how much money you currently have. It doesn't depend on any attribute about you other than the fact that you possess this token. Somehow you came to possess this token, now you may ride the subway. So this is a model that was first explored in the 1970s, and it's had some impact on programming languages ever since. Things like references in Java or JavaScript are kind of a capability in that you can't do pointer arithmetic and make them up. It's something somebody has to give you this token that says you're allowed to do stuff. But you could also think of these as cookies that you get from a website, or references in languages, or file descriptors are almost a little bit like capabilities. So file descriptors. You can open a file, and here is, going back to our Chromium case, you open, in this case, a font directory. And what we're doing in capability mode is we say that you are not allowed to acquire these new references to things, new capabilities. You can't just make them up. You can't just ask the operating system for them either. We say any access to a global namespace, which includes things like the file system, but also includes things like network interfaces. Any access to a global namespace is cut off completely. You cannot open new files. But what you can do is have somebody delegate and pass them to you. So somebody else who's more privileged can open that font directory and then hand it off to the renderer process because the renderer process needs it. So we have done this capability mode. This is kind of one of the two parts of Capsicum. The second part, which is kind of the part that took a lot more of the work, is the idea of partial delegation. So a file descriptor is a bit like a capability. You can't just say write to the number 4. You first have to have the number 4 have some meaning to the operating system. However, if you open a file read-only with O_read-only, you might think, excellent, that's a read-only file. I'll hand it off to my sandbox browser process or renderer process. And the renderer might not be able to write to the file, but it can fchmod it, which is probably not what you meant when you said this is a read-only reference to something. And therefore, what we do is we impose more limitations on file descriptors. We have very, very fine-grained ways of saying what you're allowed to do with a particular file descriptor. So you've opened it and you've passed this around, and now you can restrict that so you can only read and seek on a file descriptor, for instance. Or there are all kinds of other rights that you can also delegate. So yeah, you're not allowed to fchmod in this case. And this partial delegation also works nicely with the at family of system calls, things like openat and fchmod at, where here is an example of a subset of a file system hierarchy. And the renderer process in a browser needs access to these fonts. So what we're able to do is open a directory descriptor for just this top level directory, and then it can use the at system calls relative to that root, and it's just not allowed to use ... to go back up and escape. So we applied this to Chromium, to a large web browser. And one reason that we wanted to use Chromium was because it was already a case study of all of the possible ways that you could do sandboxing at the time on a bunch of different operating systems. So you can see on the Windows case, well, people in this room, again, may not be very surprised to see that the Windows case doesn't fare very well. So in Windows, it is possible to put a process into a state where if you don't give it a security label, then things that it accesses that have security labels, it's not allowed to access. So that sounds pretty good. The trouble is, in Windows, there are a lot of things that don't have security labels. And that includes things like the network card. So it's like, well, that's very nice that you can only access my flash drive that I've plugged in here, and you can access my VPN, but you can't access the files under C program files. Ooh, that's very exciting. And as you can see, it was also extremely complex to implement. On Linux, we have a slightly different story. So the Chroot sandboxing model is quite popular, but it's also actually quite porous. Now, if you start using POSIX network namespaces, then maybe it gets a little bit better. But of course, the other problem with the Chroot model is you have to have privilege. So in order to protect yourself from exploits within your program, first, you have to have part of your program be setuid root, which doesn't seem like a great idea. The SE Linux policy version, which I think has now been deprecated in Chrome, in fact, that really also didn't work out very well, partly because you're not able to, with a static SE Linux label, you're not able to say this is one sandbox and this is a different sandbox, and I want to create a bunch of ephemeral sandboxes. All you can say, this is of type sandbox T, and then they're all in the same security, or they all have the same security label, which means one can do things to the other, which is not really what was intended in the first place. Not a lot of code was required. However, it turns out that in order to write an SE Linux policy, you actually write something in a macro language that expands to a massive SE Linux policy. And the only way to do that in a sensible, sane way actually grants way too many rights. But nobody notices, because nobody complains when you're allowed to do the things that you wanted to do, as well as other things. They only complain when you're stopped from doing the things that you wish you could do. SecComp is an interesting model. So the original SecComp, where you just had 3 system calls available to you, in some ways, is a little bit capability oriented. You have files, and you can read them, and you can write them, and you can close. How exciting. The trouble is that in order to get any meaningful work done, the developers of Chromium had to write over 11,000 lines of, much of this was like 2,000 lines or something of handcrafted assembly, all of which was absolutely security critical in order to forward system calls out to the browser process. And so this desire to really clamp down sort of backfired. And that has since led to SecComp 2, which I could perhaps talk a little bit more about in a bit. On OS 10, the sandbox model based on a mandatory access control framework, which originally actually came from FreeBSD. It's sort of okay. There are some restrictions when you're doing, or there are some IPC primitives that you can't restrict, and yeah. And unsurprisingly, the system that we developed has all the green checkboxes. Isn't that fantastic? But the reason for that is it's not just a glib bottom of the slide thing. It's the observation that the discretionary access control model, the owners and things that they own model, isn't a great fit for trying to do this kind of sandboxing where you take an application running as one user and split it up into a bunch of bits. But neither is the mandatory access control framework, which is the SE Linux approach and the Apple sandbox approach. It's really not actually a very good fit because that's excellent if you want to talk about, well, I want to keep my secret users from reading top secret data, some system administrator provided policy. It's a great fit for that, but it's really not good fit, again, for this application sandboxing model, where it's this capability-oriented model, and when you think of it in language terms of references and things, that actually is a pretty natural fit for decomposing an application into objects that can't access things inside of each other. So to give a kind of a more concrete example of how this all works, let's take a look at TCP dump. Now, TCP dump is a great application because it parses all kinds of arbitrary code, or sorry, all kinds of arbitrary network traffic. The parsers are written by who knows who, and it often runs with privilege, And it's your eyes and ears in the network. So you say, oh no, there's an attack. There are weird packets floating around my network compromising systems. I will run TCP dump as root and point this arbitrary parsing code at it, and then we'll see what happens. And this is often what happens, and it's often not, it's often not a great idea. So this, I'm going to talk about some changes that we've made to FreeBSD, or to FreeBSD's import of TCP dump, and you can see these things in head at the moment in Subversion, or if you prefer Git, there's a Git SVN clone. Right, so here is the extremely simplistic, overly simplistic model of what's going on in TCP dump. So you set up a filter, and you get some stuff that comes into TCP dump, and then you parse that stuff, and then you spit it out into a file. Now it's actually more complicated than that, but still. And so in this model, if you see a nasty packet that contains some data that will exploit a vulnerability in one of the many, many, many parsers that's been written for TCP dump, well, that goes into your network card, and then that exploits the parser here, and then, okay, well, you corrupt the output file. There's no getting around that. If your parsing code is incorrect, the results of your parsing are not going to be right. The trouble is, of course, that you are also able, as root, to access all kinds of other crazy stuff that you would like to not be true. And so what we've done is applied Capsicum here in order to limit the privileges that TCP dump has access to while it is running. So on the stack, we have to put some more stuff, not very much. We have put a little structure here that says the rights that you're allowed to, you'll see what that structure is used for in a moment. So we limit the PCAP input device here. So this ifdef under FreeBSD, this is in our vendor import or contrib import branch. And then you can see here's basically the difference required. So what we do, we declare the ioctls that we might want to use. We set up that write structure to say, okay, you're allowed to do an ioctl, and you're allowed to read from that device, and then we actually limit that file descriptor to those writes. So with that file descriptor now, you're only allowed to do ioctl and read. You can't write to it, for instance. And then we also limit which ioctls you're allowed to do. And this has to be done this way. It can't be done in a sort of global system call way, because the ioctls, which ioctls you are allowed to use in the interpretation of those numbers depend on what device you're talking to. So this limits that input interface. So you're no longer allowed to just write stuff back, or you're not allowed to do ioctls that we don't want you to be able to do. So this is in the setup phase before you start processing the untrusted data. Then the output is this dump file. And again, similarly, we're going to set up that temporary structure to say, well, you're allowed to create a dump file. You're allowed to do fcontrol on it, truncate it, a couple of other things, and of course, write to it. And that's it. And then finally, we enter capability mode. So first you do some setup, you initialize things, and then you limit yourself so that you have your input, your output, and you can only use them for those purposes. Then you enter capability mode. At this point, TCP dump is not allowed to open any new files. So at this point, if you see that evil traffic and you managed, well, we have put this barrier around so that if you manage to compromise the packet parsing, well, you're still able to corrupt the output file because you're allowed to write to the output file, but that's it. You certainly can't do arbitrary things in memory or on disks or whatever. You can't access other applications. You can't do things as root that you otherwise might be able to do. Now, that's a very nice, simple model, but it's actually slightly more complex because, well, sometimes you're reading from an input file because you want to record stuff and then you want to read it. So we do a similar sort of thing as for the BPF, except this time it's much simpler. You just get cap read on that file. Or sometimes you want to write to multiple output files because you actually have a directory and you want each dump file to be so large and you rotate and that sort of thing. So again, using Capsicum, this is a fairly straightforward thing to do because we can give you a capability to the directory. So in this dump info struct that we have in TCP dump, well, we just add a file descriptor for the directory, and we arrange for you to have the appropriate rights on that directory only, so that then later we use openat rather than opening a new file with the normal open system call. So you're allowed to write stuff in that output directory, but you're not allowed to write stuff anywhere else in the file system. So that looks pretty good. And then the question is, all right, well, are we all done now? Well, at this point, if you parse the packet and something evil happens, you exploit a vulnerability, you can write into the dump output directory, and that looks pretty good. And for FreeBSD 10 at this point, we're done, because this is as far as we kind of can go. But the trouble is there's a limitation when it comes to name resolution. So if you change your name server partway through execution or something, there's no way to open a new socket to talk to the name server and resolve names. So this is an example of the kind of problem that larger, more complex, higher level applications tend to have. And this is why something that Pavel is working on at the moment, and has done a lot of work on, and you can see it in head at the moment, is a service called Casper, the Capability Services Provider, also known as a friendly ghost, a little bit like a daemon, but a ghost, I guess, slightly different. And the idea here is that we provide what is, in some ways, almost a cross between a runtime linker and dbus, a service that provides these higher level services that itself understands how to limit those services. So in the TCP dump case, you'll see code that only applies for FreeBSD 11, the current in head, where if we have this capability DNS provider, then instead of doing get host by adder in the normal way, we will do it proxying through Casper. Well, rather, we'll ask Casper to give us a handle to the capability DNS provider, and there we go. And this is how we get access to Casper in the first place. Before we enter capability mode, we can simply talk to Casper, and we have ambient authority, so it lets us do that. And then we can open services, and then we can limit what we do over those services. So much like the kernel API for Capsicum provides a way of limiting file descriptor access and narrowing the interfaces that you're allowed to use, in a similar way, Casper does this for services of a more abstract nature. You write a service, and it has a number of methods, and you're able to restrict access to those methods. So this way, you're able to map higher level ideas about program rights down into lower level software. So what's next? Well, currently, there are a bunch of people who are working on this stuff. So in Cambridge, this was kind of started by Robert, and then I came along and joined him. And then some folks from Google got involved, and they did some work and helped us write a paper, among other things that did fairly well. Google has also funded Pavel jointly with the FreeBSD Foundation to put this into more base system applications. So we now have lots of things in the FreeBSD base system that are using it. And we also have a guy who's working at Google pretty much full-time on a Linux port. And so in some ways, and I'm leaving Cambridge and going to Canada, so hi, bye. I guess it'll be harder for me to come to FOSDEM in the future. I'll take longer or something on a plane. So it's being used in a number of places, but we are quite interested in acquiring more platforms and in more targets. So obviously FreeBSD. The Dragonfly people have been looking at the APIs, and we've been kind of going back and forth and talking about stuff. Just last week, actually, it was announced that the next version of OpenSSH has Capsicum support on any platform that provides Capsicum support, which currently is just FreeBSD, but others in the future. And there are a number of other interesting people and companies that we talk to who are interested in this sort of thing. But we're very much interested in getting this API into other places as well. So the Debian KFreeBSD people will kind of benefit from it almost for free, because they're already running a Debian user space on a FreeBSD kernel. But the Google Linux port, we would quite like that to kind of happen, and we'll see. I mean, there's a certain amount of track record with Google getting patches into Linux, and there's also a bit of track record with Linux developers saying, that's a good idea. Let us write a completely incompatible API to do a very, very similar thing. And that's the sort of thing that could possibly happen. But we're also interested in more targets, things like, so lots of FreeBSD base system applications. We would like it if every base system application or every network-facing daemon used Capsicum to protect itself, because basically anything that accepts untrusted content, and that is anything that talks to the network, among other things, could be exploited if something goes wrong. And so we'd like all of those applications to use these protections. We'd also like to upstream things that we have done, and it would be great if more upstreams like OpenSSH were to adopt Capsicum for those platforms that support it while we work on getting more platforms to support it. We're working on the chicken and the egg. But also, in the vein of Casper, we're really interested in how you can map these low-level security concepts into higher-level application frameworks. So I did a little bit of proof of concept work when we were first doing the Capsicum thing with Qt, so that you could write a little Qt text editor sort of thing that was completely oblivious to Capsicum, but the Qt libraries understood Capsicum and sandboxes and how to ask for privileges through another mechanism and that sort of thing. And so that was great. And so that kind of cute stuff would be nice. And also, KDE is an interesting opportunity because the KIO slaves framework is actually a really, really good fit for this kind of protection where you say, here's an IO slave that's going off and speaking some network protocol, and it would be nice if that IO slave exploded if it didn't get to do anything that I get to do, but instead it just gets to corrupt the file that I get back or that sort of thing, in which case you need to have another exploit in order to do arbitrary things as me. And so really, we're interested in more people adopting and using and collaborating. So this is the web page where, oh, that's supposed to say viewers like you, but I guess you can't really see it. So there's the web page, and there is a mailing list, and from the web page you can get to all of the code and talk to friendly people who say, yeah, we would love to help you understand how Capsicum can be deployed in various places, whether it's in applications or whether it's in distros or what have you. And so, yeah, thank you for listening. See a question.
You mentioned that you had something to say about SecComp2, so please do so.
Right. So SecComp2 is this kind of more sophisticated model of doing SecComp kind of stuff where you can write like BPF-style descriptions of the system calls that are allowed, that sort of thing. So the two pieces of Capsicum, one is the restricting what system calls you can interact with, and the other thing is restricting what you can do with a file descriptor. And so SecComp2 is something that allows you to do the first, basically. When it comes to, so David actually tried to use SecComp2 as the basis for the Linux Capsicum support. But the problem is it's basically a system call wrapper framework. And any system call wrapper framework, there are limitations around time of check to time of use, vulnerabilities and that sort of thing. So he did a lot of work in order to try and make SecComp2 support this sort of functionality. But in the end, it makes everybody uncomfortable because there's no way to know that you've got it right kind of thing. So one thing that we were able to do by doing surgery deep in the FreeBSD kernel is we could say, okay, here's the fget function. This is the one place that you turn a file descriptor number into a pointer to struct file. Therefore, if we change the signature to that, the compiler will tell us if we haven't changed all of the rest of the code, that kind of thing. And so techniques like that, they require surgery deep in the kernel, but on the other hand, they allow you to have a fair amount of confidence that you've got all the corner cases. And the SecComp2 model, yeah, it's harder.
So you went through the example of how you ported TCP dump to use Capsicum, and it didn't seem too complex, but to make it even easier for future other programs, are you guys planning or developing a tool that can, say, statically analyze the syscalls that a program makes and sort of suggest things that you can do to use Capsicum?
It's funny you should ask that, because actually, yeah, a colleague of mine, Kevin Goodka, who is in the next office to me at Cambridge, is working on a static analysis framework that allows you to annotate code and say, I think this code is dangerous, I think this is sensitive, I think that I might put some kind of sandbox boundary here, and that sort of thing, and then you can ask the tool, have I satisfied the policy that I would like to have before I actually do all the work of converting things for sandboxing. The other point about TCP dump, it is a very simplistic example, you're right. One thing that it does nicely is that it does everything that requires privilege first, and then it does untrusted stuff, or it does things with untrusted data. Anything that fits that model is really easy to sandbox. Anything that's more complicated because you're continually doing new things and you can't statically declare them, that's where you have to have some kind of runtime support, something like Casper, which can get you new privileges as you require them.
Okay. Further questions? Yeah, I'm running up. Oh, staying down first. Ladies first.
How much modifications did you do into the kernel? And was it mostly at the boundary, at the physical boundary, or was it at the low level?
So I guess I don't need to repeat the question, everybody. Yeah, you have a microphone. It's only I who can't hear your microphone. Yeah, so the changes were, they touched a lot of places in the code, but they weren't extensive changes. So for instance, the fget change that I described, we basically said anywhere in the kernel that you do an fget, you now have to do an fget that declares what rights you're supposed to have in order to do this fget. So if you're doing an operation that is morally reading from a file, then you have to change your fget signature to also have cap read in it somewhere, that kind of thing. That caused a lot of diff, because we use fget a lot anywhere you interact with a file. It caused a lot of diff, but the diffs were all very, very simple. There were other things that we did which were, I don't know, a little bit thornier, I guess. So we modified the name lookup stuff in order to make sure that the openat relative to a capability stuff would work correctly. In particular, we basically had to disallow ... when you're in capability mode because absent a universal locking scheme, which would have to include like remote NFS servers and things like that, there's a possibility of a race where you could get out. So we had to do some work there to disallow things. Some work in like the runtime linker, yeah. But mostly in the kernel, it was kind of infrastructure stuff, which is either the thing that takes a list of system calls and then generates the code that handles the system calls, or things like declaring rights that you need, which is a small change times many hundreds of places, and that kind of thing.
If the program has restricted access through Capsicum, do these restrictions survive fork and exec system calls?
Yes. So when you enter capability mode, you can never leave it. It's like the Hotel California, I guess. And when you fork, your children will also be in that same state.
Okay, so for example, you can run Capsicum unaware programs already inside Capsicum by like integrating support in the shell or something like that, right?
I think I couldn't quite. I mean, I heard integrated support in the shell. But
running a program sandboxed, running Capsicum program which is unaware of running program which is unaware of Capsicum inside a Capsicum sandbox by the means of restricting access by the caller program.
Right, yes. So it is definitely of interest, and we've done a little bit of infrastructural work to do that. I'm currently poking the runtime linker to make it possible to run dynamically linked applications, start them from within a sandbox. Basically, instead of giving it an LD library path, you give it, or you open the directory descriptors for the library path, and you put that in an environment variable, and then you exec, and then it's able to go off and find libraries that way. And with that, yeah, there's definitely a big interest in the group of doing a capability-aware shell where you could run lots of command line utilities, particularly the simple ones, but even some of the not so simple ones you ought to be able to run without them ever having to see ambient authority. And that would also be really nice if you're trying to do things like reproducible and deterministic builds, because it's like, well, I can actually say definitely for sure these are all the files that the compiler accessed, and it wasn't secretly going into user lib something 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 that I didn't know about. You know, that kind of an approach.
There was another question here. Somebody here? Oh, okay, I'm going to run over there.
So sandboxing is, let's say, easy. Sharing is hard. So what Capsicum does in respect to sharing between sandboxes?
Right, so you have access to all the normal Unix IPC primitives so long as you set them up in a certain way. So either, you can open sockets, Unix domain sockets, and pass descriptors over them and stuff, but if you're accessing anything in the namespace, then you have to have done that in advance. You can still do anonymous shared memory segments and that sort of thing. I mean, you can, from within a sandbox, you can create a shared memory segment so long as it doesn't have a name. If it's an anonymous shared memory segment that's only referenced by file descriptor, and then you pass that up to your parent, and then your parent, so you can set up communications channels like that. You can open the door as wide as you want to, but we want to start with the door being closed. So you have to be explicit about the things that you want to share rather than just implicitly assume they're available. So yeah, a sandboxing mechanism by itself is not the whole story. You still have to write the code to do useful things and communicate with other bits.
I just wanted to compare a little bit to AppArmor running on Linux, and I have two questions about that. Many distributions that actually run AppArmor also have a small profile to run TCP dump, and I was wondering if you've ever done a comparison between that and the one basically sandboxed by Capsicum. And in addition, I was wondering if at all it would be possible to have Apache support for Capsicum in a reasonable time frame.
Right. So on the first question about AppArmor, we did our main comparison of a bunch of different things in the context of Chromium just because it already had all these different mechanisms. The thing about AppArmor, and it's basically in the same category as SE Linux for this purpose, is that you have to have a policy that you can describe statically. So you can say TCP dump is only allowed to output files into this directory or something, but what you can't do is say TCP dump is allowed to output files into the current working directory or something like that. So a dynamic policy like that is much harder to express with those tools. Yeah, I mean, the internal protection thing, if you had a process-based NPM for Apache, that's the sort of thing where it is a more, I mean, I guess it's a debatable point, but I think it is a much more natural fit for Apache to say, I'm going to start this worker, I'm going to start it in capability mode, and I'm going to give it access to this thing and this thing and this thing, as opposed to trying to write some global policy definition where you have to change your Apache configuration, and then you also have to go change your AppArmor stuff to say, well, and then a worker that has this security label attached to it, which you then also have to do elsewhere, is only allowed to get things from var www/mysite1 or whatever. Yeah, so I have not hacked Apache NPMs myself, but it is the sort of thing that should be doable. I have colleagues who've hacked on Apache more, including Ben, of course. But yeah, so I think it should be a fairly good fit, but nobody's actually done the work yet.
Okay, next question. Nobody? Okay. Oh, yes.
Thank you. Hello. First of all, I'm very impressed by the work you've done, but it's maybe a strange question, but I think that adding Capsicum is to a program is adding complexity, and complexity leads to misunderstanding, and misunderstanding into threat. What's your point on this statement?
On Capsicum adding complexity and complexity being the enemy of security. So basically, well, first of all, in the applications, it really doesn't add much complexity. I mean, for Chrome, which is a fairly complicated application, we added 100 lines of code, which just said, take these file descriptors that we already have open, limit them, then enter capability mode. In the kernel, we have we had a big diff in the kernel, but it didn't actually add a lot of complexity. There was a bit more declaration of intent where you had to say you must hold the mmap capability, or you must have the mmap right on this file descriptor in order to open it, that sort of thing. Yeah, there was restriction. We were very careful to only restrict things, never to open them up more, and so it is a composable model in that way. And actually, it didn't really make the kernel significantly more complicated. This is one of the reasons, actually, why the Linux port based on seccomp2 gave us so much hesitation and so much pause, because it did add a lot of complexity, because David had to add this whole framework for doing time of check to time of use, race condition checking stuff, where you would hold on to additional things that you otherwise wouldn't and then release them at the right time. But there were several points where it could be the right time, and there was a lot of complexity that was required. And so this is part of why we were quite concerned about that approach.
Enough answer?
Okay. Any more questions? No.
And I guess further on that point is, so on the complexity thing, we made quite simple changes to the FreeBSD kernel, and we'd like to make exactly the same simple changes to the Linux kernel. However, that involves things that aren't a Linux security module. And our current read of the situation is that might be politically very difficult to do. But it could be that we can get a distro interested in applying patches and saying, actually, these are simple, much simpler patches, less complex, and they add an important security benefit. Hooray.
More questions? No more questions? Okay. Thank you very much.
Thank you
for your answers.